Hello everyone, welcome to this term project report submitted by Anwesha Patel, Ritvik Dhawe and Sambhav Jena under the course Vibration and Noise Control. The topic chosen by us is vibrations around us. We have taken into account several instances where vibrations play a key role in our surroundings and modeled a small report on this. The first instance that we have taken into account is a quarter car model. It is a mathematical model that abstracts a vehicle suspension system into its most basic form, dividing the vehicle into four distinct components: one wheel, one tire, a quarter of the sprung and unsprung masses of the vehicle. By examining the quarter car model, we can gain insights on how different suspension configurations and parameters such as spring stiffness, damping coefficients, etc. influence the vehicle's ride comfort, handling, and stability. Here, the sprung mass refers to the body mass of the vehicle. The unsprung mass refers to the tire and axle masses. The spring constant Ks and damping coefficient Cs combination represents the suspension, and Kt represents the tire stiffness. So this here shows the free body diagram of the quarter car model. As we can see, there are three forces acting at the unsprung mass and two at the sprung mass. Here R represents the road input, and we have a 2 degree of freedom system. And these are basically the equations that are governing the working of this model. Now let us take a look on how the system works. So basically this is a MATLAB model that we have designed based on the quarter cars model. And here this loop represents the sprung mass system, and this loop represents the unsprung mass system. Ks is the stiffness constant of the suspension system, and Cs represents the damping coefficient. Kt here represents the tire or axle stiffness. And here we have applied a step input. As we can see, this is the step input that has been applied, and after running the model we can see how the damping works. So as you can see, initially there is a big rise in the output value, and slowly it gets dampened to the initial input value. And here we can see the acceleration value as well. And this is the response at the unsprung mass. So this was all about the quarter car model. Now coming to the second instance that we have taken into consideration is a simple vibration absorber. In this case, the strategy for minimizing vibration in a structure that is excited at resonance. So when a machine is basically excited at resonance, the vibration amplitude is much larger, and it helps us to understand in general how the modes or resonances of a system move when we add parts to it. So in this case, we have defined a simple 2 degree of freedom system, and these are the basically the equations of motion that govern the working of the system. We have the mass and stiffness matrices in the left hand side and the forcing on the RHS. We can assume that the response in steady state will have the same equation as that of the force, and thus the given assumption has been taken. Now let us take a look at the MATLAB model for this vibration absorber. So this is the code that we have written for the vibration absorber, and as you can see, this is the frequency response for x1, x2 and as well as x1 with no vibration. The X1 is the frequency responsive. This is a 1 degree of freedom system, and after adding the second system X2, we have split the resonance into two peaks, and now we have the anti-resonance. Now if we change the damping value to 100 times larger the present value, yeah, so after increasing the damping value to 100 times the larger value, we can see that adding the damping lowers the height of these peaks for both the resonance and anti-resonance cases. And in case of an ideal damping scenario, it occurs when the peaks are low but not so much that they can ruin the absorber frequency. So that was all about the vibration absorber. I would like to hand it over to my teammates.
Tuning fork is a small metal instrument consisting of a stem, two prongs, and a footpiece that produces a constant pitch when either prong is struck against a firm and resilient surface. It is usually made of steel, magnesium, or aluminium that is used to tune musical instruments by musicians and now used by doctors to assess hearing. From the mathematical relations defined here, we see the dependency of frequency on different geometry and material parameter. In order to study that, we have prepared a model in SolidWorks and ran a frequency study. The study gives us values of amplitude, frequency for different measures of length, area, and material property. Proceeding with different changes, we successfully generated four different vibration modes corresponding to different frequencies and amplitudes. The snapshot of different results and deformations obtained is presented here, along with the different frequencies we observe. The animation is as seen. Thank you.
So moving on to the next part of our vibration storm project, we try to model the kinematics and dynamics of IC engine piston crank mechanism. So as we know, IC engine is a heat engine in which chemical energy of fuels is converted into the mechanical energy in form of rotation and torque, which is then transmitted to the wheels. So as we know, the piston crank mechanism lies at its heart. So we see a piston which exhibits reciprocating motion, which is then reflected in the as the rotatory motion of the crankshaft. So following the usual process of calculations with relations for the fixed length of the connecting rod as well as different radii, we come up with the following expressions for velocity of piston and acceleration of piston. The thing to note here is that the n stands for the ratio of the length of the connecting rod to the radius of the crankshaft. So it's basically L upon R. So this basically highlights the procedure. So we take geometrical relations in which the length of the connecting rod is assumed to be fixed, and we model the entire mechanism as a slider crank mechanism, which helps us to obtain simplified expressions for the position of the piston with the rotation of the crankshaft as well as its velocity. Like using the Lagrangian approach, we can model the equations for the reciprocating motion as well. So in order to have a look at the dynamics, we model the same setup in SolidWorks. So as we can see, this shows the piston and crank mechanism. As the crank rotates, the piston exhibits reciprocating motion, and as the piston exhibits reciprocating motion, the crank rotates. So this model helps us to visualize the motion better and comprehend the kinematics that goes behind it. So like I mentioned, the reciprocating motion of the piston is transmitted into the rotatory motion of the crank. So, and this simple mechanism is at the heart of IC engines, which is at the heart of every combustion vehicle. So our key objective was to model the dynamics of piston crank mechanism, which is commonly a part of IC engines. Thank you.